say before I get to the body of the talk is just to kind of situate this maybe a little bit in the context of like a lot of the work that's been happening in quantum gravity and philosophy of quantum gravity in particular, where people have wanted to talk about spacetime emergence. So one thing that, as metaphysicians, we're like, what can we learn from quantum gravity? And, there's this kind of, it's in some sense like, well, we're not really ready to draw metaphysical conclusions from quantum gravity because we don't know yet what is a right kind of approach to giving a quantum theory of gravity. There are a lot of different approaches. But one thing that people have been optimistic about is even though there are a lot of different approaches, there might be some kind of convergence on certain themes that you're seeing coming from the different strands. And one that some have said is that, well, whatever kind of approach you pursue, it's going to turn out that space-time is emergent. And the philosophical work that I've read and been really inspired by, especially following from these big projects Nick Huggett and Chris Wuthrick have had over the past decade or so, have really focused, I think, here on cases of loop quantum gravity or causal set theory. There's some work on string theory focused especially like Nick's work on T-duality suggests that in all of these cases, space-time is emergent. I'm going to be looking at more work in the context of ADS-CFT correspondence. And so I think if this is right and the kind of the physical results here aren't really suggesting emergence, then maybe we can't, metaphysicians, there's a kind of another pessimistic kind of conclusion that we can't even draw that conclusion. So that's just the kind of, and this obviously isn't like an idiosyncratic or marginal kind of line of research in quantum gravity. So that's just, I'm not going to come back to that larger kind of conclusion here. I'm just going to be focusing on these particular results, but I just wanted to say something about that. Oh, last thing I should just say, I posted the paper here. This is going to, so if you want more references, I'm going to be talking about a lot of results and just kind of going through the details super quickly, just in the interest of time. But there's like a little more discussion here. More importantly, there's like a longer bibliography if you wanted to learn more about the results I'm going to be talking about. And this paper is forthcoming in the Philosophy of Spacetime volume that Nick and Chris are putting out probably next year, I guess. Okay, so let's see. Right, so as I said, a lot of the work that I'm going to be talking about here is in the context of ADS-CFT correspondence. So this follows on the paper by Maldacena in '97, where he was looking at a series of different pairs of theories. One theory always being a higher dimensional gravitational theory describing an anti-de Sitter ADS space-time. And then a lower dimensional, so we could say d-dimensional conformal field theory. He established a kind of translation manual between these two theories, and this is later described by Witten as giving us a kind of holographic theory. So you can think about the d-dimensional theory as lying on the boundary from where, lying on the boundary of this higher dimensional anti-de Sitter space-time that's described as being in the bulk. Now, so far, several philosophers, a lot of philosophers have talked about ADS-CFT correspondence, and I'm not going to be just talking about it in general. I want to look at a particular line of research that comes out of this, but I just want to note that many philosophers, when they've looked at this, and Karen talks a little bit about this in her dissertation and in her book, and draws this kind of conclusion that just from the duality itself, you don't get a claim of emergence, although a lot of people, physicists, talk about ADS-CFT giving us a reason to think that space-time is emergent because, it seems like a promising way to have a non-perturbative quantum theory of gravity. You can just derive the facts about what's going on in the bulk space-time from non-gravitational degrees of freedom on the boundary. Just the fact that you have this kind of correspondence or duality says you can go back and forth, but that's compatible really with a lot of different metaphysical options. It could be that either theory, yes, the non-gravitational theory is fundamental and then the gravitational degrees of freedom are emerging from them, but it could be that they're both fundamental. It could be that neither is fundamental and they're both ultimately arising from both sets of facts are arising from some more fundamental physics. So, that's a kind of conclusion I just want to note that many people have said, and I agree with about ADS-CFT in general. Some have thought that these kinds of results that I want to talk about, where now we're going to be talking about some specific kinds of facts on the boundary. So in particular, those using quantum information theoretic concepts like the entanglement entropy are giving us a connection between what's going on in the boundary and the metric, the facts in the bulk, that are demonstrating that there is not just a correspondence or a duality here, but really something more like emergence. And so I'm going to come back to like people that have said that. So well, first I just want to say a little bit about the kind of concepts I'll be using. So I'm going to be focused on work that establishes a connection between metrical properties inside the bulk and inside the ADS bulk, and facts about entanglement entropy on the CFT boundary. Later on, I'll be talking about results that are outside of the ADS-CFT correspondence, but I'm going to start with that. The kind of concepts that we're most interested in to begin with is the concept of the Neumann entropy, S rho, where rho is a density matrix. And this is just a quantum analog of the classical information theoretic concept of the Shannon entropy. So this is kind of one way, that's a kind of natural, a natural way of formulating the Neumann entropy. What we're going to see more often in the paper, in what follows, is kind of this way of capturing the Neumann entropy for a given state. And so if the density matrix is diagonalizable with eigenvalues lambda sub I, you can compute the Neumann entropy of a state as a sum involving these eigenvalues in this way. This notion of a Neumann entropy is very simple for pure states. Pure states are always going to have zero Neumann entropy. But if you're talking about mixed states, states that are statistical mixtures of two or more pure states, then in general, the Neumann entropy won't be zero. What's more interesting for us here is if you're talking about a composite system involving two or more components, then we could start talking about the Neumann entropy as giving a measure of the degree of entanglement of the system. And so then you can think about it, S rho as the entanglement entropy for a system. So how does that work? Well, if you just think about a simple bipartite system, we could call AB, so a pair of electrons or photons or a pair of qubits. Just start by simply assuming that it's in a pure state. So for the bipartite system, its Neumann entropy will be zero. Then we can start asking about the Neumann entropies of the components. So if they're in a product state, if the total system is in a product state, so A and B aren't entangled with each other, then again, their entanglement entropies will be zero. But if they're entangled, then this Neumann entropy is able to give us a measure of how entangled the system is. And depending on the degrees of freedom of the system, there'll be a maximal state of the entanglement entropy associated with a maximally entangled state. So for a system of qubits, that'll be the Bell state. So this is the notion of entanglement entropy that we'll be using. There are other ways that we can quantify the degree of entanglement of a system. I'll be talking about some of those later on, but the entanglement entropy is a core notion that we'll be focused on. So right, so the main result that I'm interested in that comes up a lot when people start talking about the emergence of space-time from entanglement entropy, from facts about entanglement, is this result from Shinsei Ryu and Tadashi Takayanagi in 2006. So let me just go back to this picture quickly. So this kind of simplest cases that Ryu and Takayanagi talk about is where you're thinking about D is 2. So you've got a 3-dimensional anti-de Sitter space-time, and then you're considering, so the surface, the conformal field theory lies on a 2-dimensional surface. bounding that three-dimensional space-time. And so in the Ryu and Takayanagi paper, the kind of simplest cases they consider look like this. So you can think of the whole space-time as a cylinder, and this kind of vertical dimension will be relative to some foliation. You can think about that as the time dimension. And they want us to consider a static slice through the ADS bulk. So that's what this picture is supposed to be here. So imagine that you have this static slice, so this static slice through the ADS bulk, and imagine cutting it up into two regions. So you make two cuts here at the top, and that's going to, and the bottom, and that's going to separate out two regions. So you have A on the boundary, and then its complement. And what they say is you can take a geodesic that connects those two cuts through the bulk, and that'll be what they call the minimal surface or the extremal surface through the bulk, gamma A. And what they do in the paper is they make this conjecture, which is that there's a very simple relationship between the entanglement entropy of this state on the this CFT state A and the area of this extremal surface, gamma A. And it looks like this. It's just the entanglement entropy of A is the area of the extremal surface divided by 4 times Newton's constant. And so this is something that's established. I'll talk a little bit, actually a lot later on about why this turns out to work, why the conjecture turns out to work. But if you're familiar with work on black hole thermodynamics, you'll see that this has like a very familiar form. Sorry, I'm kind of covering up some of my slides. Oh, I can't do that. Okay, never mind. So you'll see that this has a really familiar form. It looks just like the Bekenstein-Hawking law for black hole entropy. And indeed, when Ryu and Takayanagi make this proposal, they're explicitly making this proposal because they think, well, a kind of standard way of explaining. So in the 80s, Raphael Sorkin and his collaborators made a proposal to say, well, why does this Bekenstein-Hawking law work, connecting the black hole entropy with the area of its event horizon? The explanation worked by interpreting black hole entropy as a kind of entanglement entropy. And so Ryu and Takayanagi say, okay, here's another situation where we're dealing with entanglement entropy, and we want to understand in terms of these entanglement entropy facts about these surfaces through the ADS bulk. Let's make this kind of conjecture and see if the same relationship holds, and lo, it does. So I want to talk just a little bit about this work and how influential this has been. So like I said, Ryu and Takayanagi, they focus on static slices of the ADS spacetime in order to establish this entanglement entropy equals area of the extremal surface over 4G law. This was quickly followed up by a paper by Veronica Ubani and Mukund Raghumanian and Takayanagi, again, generalizing it to general kind of slices through the ADS spacetime extremal surfaces through the ADS spacetime, which provide a covariant account of the distances in terms of entanglement entropies on the boundary. So you have a way here of recovering from facts about quantum information theoretic facts, facts about the distances, facts about the metric. This work, in turn raised the question of how much of the ADS metric, how much of the metric are you able to recover just by knowing facts about entanglement entropy? And the answer is well, actually quite a lot. So Cindy Keeler and her collaborators, Bao, and so on, describe this as a project in bulk reconstruction. They want to understand how these degrees of freedom, which are well understood from the perspective of non-gravitational quantum field theory, reorganize themselves into a manifestly local gravitational theory. And so I just want to describe a little bit of this so you can kind of see how it goes for those who aren't familiar with this work. So, one issue, so the Ryu and Takayanagi result can give you, if you're considering regions that go from one part of the boundary to another, how you can recover facts about their lengths just from facts about the entanglement entropies on the boundary. But you might ask, well, can you recover the areas of closed surfaces that are embedded in the ADS bulk? And so this work on holography did that, or does that. And so, I mean, it's still kind of controversial what is the right way to do this, but one way that you can recover facts about the areas is you can start by finding geodesics that are tangent to these regions on the closed surface, and then extend them all the way out to the boundary. So if this geodesic is K, then this the state on this part of the CFT boundary you can call I sub K, and you can kind of keep doing this all the way around. What this work, argues is you can use that to define a notion of the differential entropy that's given in terms of the entanglement entropies of these regions on the boundary, and then view the area of this closed surface as equal to the limit of the differential entropy as n goes to infinity. So, like I said, I mean, this is controversial. One of my advisors, it's funny to talk about as advisor, but Veronica Hubanes argued that this isn't really the right kind of entanglement measure to be using. It has certain problems, like if this closed surface is too wiggly, for example, and has argued that instead we should use what she calls a covariant residual entropy. But what we're seeing in this kind of work is a way to capture a whole lot of the metric just from the entanglement facts, or facts about using different entanglement measures on the boundary. And in the paper that I had I cited on the previous slide, or I guess it was this one. In this paper, they argue that actually you can give a unique result for the metric, at least in the areas in the neighborhood of the extremal surfaces, just by using facts about entanglement entropies and other measures of quantum entanglement on the boundary. Okay, so this has all so far been in the context of ADS-CFT duality. You might ask, well, is it possible to extend these kinds of results? And we don't live in an ADS spacetime. Is it possible in general to give these kinds of, be able to recover facts about distances or areas, metrical facts, from facts about entanglement entropies? And so there is some result in quantum many-body systems and condensed matter that has been, it's been promising that you can give results like that. So first, I just want to kind of reframe how I've been talking about these results a bit. So in classical thermodynamics, we're familiar with the idea that entropy is an extensive quantity, that it scales with volume. But what we're seeing from these results over, for example, the Ryu-Takayanagi result and the Bekenstein-Hawking law for black hole entropy, is that instead of having entropy scaling with volume, it's scaling with area, whether it's the area of this extremal surface through the ADS bulk, or in the case of black hole thermodynamics, it's scaling with the area of the black hole's event horizon. And so that's what's allowing us to relate facts about entanglement entropy to facts about distances, or facts about the metric, is that you have this kind of area law. And so this review article was really, really helpful to me. So I have a bibliography at the end of the paper, but this Eisert paper is really helpful in reviewing a lot of the work in condensed matter, kind of giving you, establishing area laws and saying when they hold, when they don't hold, and so on. But the goal is a generalization of the connection between the entanglement entropy of a region and the area of the surface separating it from a complement region. So I'll just talk about like the really like simplest case that they discuss in this paper, in a one-dimensional case. So they give the example of a one-dimensional quantum chain, where you could think of it just as a chain of discrete systems. And then again, to talk about the entanglement entropy, we're gonna say, well, we've got two systems here, right? That total system is decomposed into at least two systems. And so the one block that we'll consider is, we'll just call I, and that consists of its first n members. So if the entanglement entropy was an extensive quantity, if it was scaling with volume, then that would mean that the entanglement entropy of I would be proportional to, in this case, the cardinality of the block, right? That's its volume for the simple one-dimensional quantum chain. But instead, what we find is that the entanglement entropy doesn't scale with the cardinality of the block, it scales with the boundary. And so for the one-dimensional system, the boundary is really simple. It's just one of these members. So for example, so how do they show this? How do they compute the entanglement entropy in this case? It's actually very difficult, but just for the case of, to see kind of how this is done, for a bosonic harmonic chain, with the elements modeled as spinless particles with charge, what you'll do to start with is just write down the Hamiltonian for the system in terms of the canonical operators, X and P, and also system operators, capital X and capital P, that'll describe the coupling structure. In order to derive the area laws, they have to make the assumption that the system is local. And what this means is that the elements in the chain can only act directly with their nearest neighbors. Now, as Izard and his collaborators explain, this is still really, really difficult to compute, the entanglement entropy, even for this really simple system. But where, and in particular, this case that they're talking about is just like where you divide the chain in half. And so I is just like the first half of the total chain. Even there, it's very difficult to compute. And so what they do instead is compute another entanglement measure, the logarithmic negativity, E sub n, and that provides an upper bound for the entanglement entropy. So in this case, what they have is they're able to give this as an upper bound for the entanglement entropy in terms of log. So here, this is going to be the average value for the this system operator, and this is a kind of minimum value. So in the kind of systems they're talking about, they've got a discrete number of energy levels, and there's a kind of minimum energy level, and this is the eigenvalue of this kind of covariance operator that describes a coupling structure for the minimum, for the ground state. The important part about this result is that, like I said, the upper bound, the entanglement entropy isn't depending on the size of the system. And so what we have is an area law. And this result is extended for more complex cases where, again, we have a lattice, but it's not a one-dimensional lattice, it's two-dimensional lattice. Again, what's found is that the entanglement entropy for one part, so like, for example, the first half of the lattice doesn't scale with the cardinality, but with the size of the system, but it scales with the area of the boundary separating it from its complement. And another thing that I just want to emphasize here, and that Izard emphasizes quite a lot in the paper, is that these results are really requiring that we're assuming locality, that we're assuming that that elements in these chains in these lattices are only able to interact directly with their nearest neighbors. If you don't have that assumption, so for example, they talk about these area laws breaking down in cases where you've got systems near their critical points. When you have the locality breakdown, you don't have these area laws. Instead, you get, again, the entropy scaling again with volume. All right, so the big idea here so far is that, yes, there are area laws. They're able to be established outside the ADS CFT context as well. So we've got a series of relationships. The relationships are established. You're able to recover a great deal of facts about spatiotemporal distances if you know facts about entanglement entropies. This is true for the kind of quantum many-body systems I was just talking about. It's also true in the ADS CFT context as well. But again, as a metaphysician, I'm interested in, well, what does that tell us about the emergence of space-time? What does that tell us about whether the metric is fundamental or not, whether it's arising from more fundamental facts about entanglement entropies? And here it just seems like these relationships are compatible in principle with a range of metaphysical options. So they're compatible with this exciting, intriguing metaphysical possibility that facts about the metric are emerging from or arising from more fundamental facts about entanglement entropy. But they're also compatible with the possibility that the direction of grounding or emergence goes in the opposite direction, and that the facts about entanglement entropy emerge from more fundamental facts about the metric, or that they're equally fundamental, or that neither is fundamental and they're both emerging from some more fundamental physical degrees of freedom. So why should we think that there's emergence here? So I want to just, I have to talk about this paper. Well, there are a series of papers, but I think this is probably a good one to look at, from Van Ramsdonk, where he's arguing that, again, like I mentioned earlier, he's one of these people that says, like, if you just think about ADS-CFT duality, it's just a duality. There's no reason to think space-time is emerging from some non-gravitational degrees of freedom in the conformal field theory. There's no reason for that. But if you understand these results, when we introduce these quantum information theoretic concepts, then we have the right kind of conceptual bridge that's going to allow us to see that this is really a case of emergence, that the facts about the space-time metric are arising from or emerging from the more fundamental facts about entanglement entropy on the boundary. So he's got a couple of nice cases in this paper, so that we can talk about here. So here's on the left, this is the same, almost the same picture that I had when we were talking about Ryu and Takayanagi. So again, right, you've got this slice through the ADS space-time, and you have this region A that's got a certain, the state on A has got a certain entanglement entropy, and that co-varies with the area of the extremal surface through the bulk here. And what Van Ramsdonk asks us to just imagine, oh, sorry, I also have these little points here, so we can just think about some point that's close to the boundary near maybe like the midpoint in region A, and some other point that is close to the boundary, maybe near the midpoint of the complement of region A. And just what Van Ramsdonk asks us to do is just kind of consider what happens as we dial down the entanglement entropy. And so what will happen as we dial down the entanglement entropy is, because of the Ryu and Takayanagi result, we have a connection between the entanglement entropy of A and this minimal surface. So what's going to happen is this length is going to shrink, right? And so the whole kind of space-time is going to start getting pinched. And as that happens, these points are going to come away from each other. And so what you have is, as the entanglement entropy dials down, the points kind of come apart from each other. And so it looks like there's this covariation here. And there is, but of course that doesn't mean that the facts about entanglement entropy are, providing the metaphysical grounding for the facts about the distances, rather than vice versa. All we know, all we get from Ryu and Takayanagi is these two goes together. But in his next case, he asks us to consider, well, okay, so that's kind of what I'm kind of confused about, that, why this should make us think that there's anything about emergence. But he talks about another case as well. So the other case, in the other case, he doesn't want us to think about just one ADS spacetime, but instead two. So imagine that we dial down the entanglement entropy of A so much that by the Ryu and Takayanagi link, the area of the minimal surface here shrinks all the way to 0. What will happen is these two spacetimes will effectively pinch apart, and you'll have two different ADS spacetimes. So what should we think about in that case? So this phrase of a gluing with entanglement, that's from Van Ramsdonk. What he thinks is we can use entanglement to glue these space-time regions together. So again, imagine, let's start from the beginning again here. So imagine you've got some, bipartite system. So that's in a product state. the entanglement entropy of A and B will, if we imagine the total systems in a pure state, the entanglement entropy of A and B will both be 0 here. And effectively what we have here is this will be the description of a system in CFT, let's say CFTA, and this is the description of a system describable by CFTB. And those states, like we just saw, when the entanglement entropy gets dialed down all the way, those will correspond to dual, like separate ADS spacetimes. So we'll have two ADS spacetimes. But now, what Van Ramsonk wants to say is we can glue those spacetimes together by putting this system in an entangled state. So in particular, in the paper, he considers this entangled state, which Maldacena showed was equivalent, well, its ADS dual corresponded to the eternal ADS black hole spacetime. And this is the Penrose diagram for this. So Van Ramsonk says we have a remarkable conclusion. The state psi, which clearly represented a quantum superposition of disconnected spacetimes, right? So any one of these product states represents, he says, disconnected spacetimes, where the dual, right, is a disconnected quantum spacetime. But then when you combine them into the superposition, they may be identified with a classically connected spacetime. In this example, classical connectivity arises by entangling the degrees of freedom in the two components. So, I mean, you can look at the Penrose diagram here. What we have is, these regions 1 and region 2 are corresponding to these two asymptotically ADS spacetimes that share a common causal future in region 4. And this is kind of part of how you can see that they're, okay, well, I don't want to talk about this. I don't want to talk about this in too much detail, but the core, I think, question I have about these cases is, why are we led, just now that we've introduced concept of entanglement entropy and the entanglement between these systems, why should we be any more led to say that there's an emergence of space-time happening here, rather than, again, just a duality and a covariance? When you have a kind of entangled state like this can correspond to a connected space-time where you have distances. In this case, maybe, that corresponds to something else. One small little thing I want to say here, I don't know if Nick Huggett is here, but he pointed me to, I think it was because of this point of the paper, this recent paper by Daniel Harlow that was really nice. And one thing that Harlow was pointing out is that a lot of in kind of discussions like this of emergence of space-time, there seems to be too many theories kind of in play that it's kind of confusing where the emergence is supposed to be. But it seems like Harlow wants to say is, what we have in this case is you have a duality between the CFT description here and a dual ADS spacetime description with gravitational degrees of freedom. Then there's another issue about when you get a kind of classical spacetime description. Now we're talking about another theory. That theory may emerge from the more fundamental CFT and ADS descriptions as some kind of classical effective description. So there may be emergence there, but there's still a kind of question about, in the kind of fundamental ADS CFT descriptions, whether or not there's any emergence. And so here I'm just not seeing this. I guess that's kind of where I want to leave this here. So we need to do more work in order to establish that what we have is emergence. Again, all of these options are still on the table. We're not necessarily led just by seeing, even though these are really intriguing, all these kind of covariances and how it looks like you can glue spacetimes together with entanglement. You can kind of pinch them apart into separate spacetimes by dialing down the entanglement entropy. By the Ryu-Takayanagi result, there still doesn't seem to be support for this emergence hypothesis more than these areas. So let's get back. I think if we want to understand better why we should think there's emergence, I think we need to understand better, like what's the explanation for why the Ryu-Takayanagi result holds. All right, so it's a slightly different diagram. So again, remember what Ryu-Takayanagi did. This was their conjecture. This was a result that they established. And what they're saying is, if you want to consider any kind of extremal surface, so a geodesic connecting 2 points on a CFT boundary, we call that gamma A, then we'll see this kind of connection between its length, that's the area, and the entanglement entropy of the region on the boundary. And so the way that they establish this is they say, okay, so let's start with this, trying to compute this length. So we can write down the metric for, and again, sorry, in this paper, in the Ryu-Takayanagi paper, and then in the paper establishing a covariant analog of this by Hubani, Ragamani, and Takayanagi, they discuss a lot of cases and show how this result is robust, but I'm just going to be considering like the very simplest first case that they talk about here, and it's a static case. So we're just looking at this like one slice through the ADS spacetime. Okay, so how do we establish this? So what we can start by doing is using the metric for the ADS spacetime in order to compute the length of this minimal surface. Then, once we have the length of this minimal surface, we can use this formula, like this conjecture, and see what is the result we get for the entanglement entropy of this state on the boundary. And lo and behold, when we do that, it turns out it gets the right result, given independent results in 1+1 dimensional CFTs. So this result of Calabresi and Carty actually matches what you get when you presuppose, when you posit this area law. I mean, to do that, you have to use some bridge laws that connect concepts in the language or quantities in the language of the CFT with quantities in the language of ADS spacetime, but you get the right result. So that's cool. And you could do that again and again, and they show how you can do that again and again. But the question is, why? Well, why does that work? So that's good. That shows us that we really have this connection between entanglement. It seems like we really have this connection between entanglement entropy and metrical facts about distances in the ADS bulk. But this raises a question of why it holds. Oh, sorry, I forgot to take that out. So as I said, discussions of Ryu and Takayanagi paper often take it to support emergence, or really, it's when people want to talk about emergence of spacetime from quantum entanglement, they'll often bring in the Ryu and Takayanagi paper and say, see, you've got this relationship. But Ryu and Takayanagi in their work, they don't discuss metaphysics. I mean, when they talk about, they have a longer paper that was also 2006, where they kind of go through the implications of this. They're viewing the implications of this instrumentally. They say, well, it's really difficult sometimes to compute the entanglement entropy from the CFT side of things. So what this relationship will give us is a good way of approximating entanglement entropies. So they're not making a metaphysical point. So how should we understand why this law holds? And so what I want to say, what I think is that, as I said earlier, the result was inspired by work on black hole entropy. And so, and in particular, it was inspired by the work of Sorkin. And so Sorkin in this 1983 conference paper that gave an argument developed in this paper with Bombelli and other collaborators in 1986 that treated black hole entropy as a form of entanglement entropy. So what Ryu and Takayanagi are thinking is, in that case, we have this kind of area law that works. Why does it work? Well, there's an explanation for why it works. The explanation involves thinking about black hole entropy as a kind of entanglement entropy. And so, I think looking at that kind of explanation and how the Sorkin and Bombelli were able to argue that black hole entropy should be the area of the event horizon over 4G will help us understand why, in general, entanglement entropy should be expected to have this kind of relationship. All right, so this is the most, annoying slide with small type on it. I apologize, but it's the only one that looks like this. So the way that this works, so the Sorkin-Bombelli argument for explaining the Bekenstein-Hawking formula for black hole entropy works by first saying like, okay, let's think about the black hole as part of a larger system, right? So in general, we're talking about entanglement entropys. We have a total system, and then we're going to divide it into parts, and then we're going to, just the entanglement entropy is going to give you how much this component system is the degree to which it's entangled with what's outside that system. And so we're going to think about the black hole as part of a total system of what lies inside the black hole's event horizon and what lies outside. And then Sorkin and Babeli say, like, well, let's just consider the states of the total region in like the simplest way we can in terms of the states of a massless scalar field in its vacuum state. And we'll represent this total field as a lattice of harmonic oscillators with this density. Then what we're going to do is we're going to use the relationship that I had on like one of the first slides that allows us to compute the entanglement entropy as a sum involving the eigenvalues of some operator. So this operator lambda is going to encode the correlations between points in the lattice, internal and external to the black hole. And what Sorkin says, so the 1983 paper just kind of sketches the argument. He says, assuming a finite number of points in the lattice, the main contribution to the entanglement entropy will come from the values of lambda closer to the horizon. The leading terminus will be proportional to A over L squared, where A is the area of the surface or horizon separating the internal from the external system. And so, the question is, okay, so that's, that's why we get this law. Well, I mean, that's why you have the proportionality. It's another issue to, calculate the constant of proportionality, but that's why we have this area law. Why is that? Well, we can see why this is by considering the fact that any physically acceptable state of this field will be a Hadamard state, right? So, Wald argues in his text on quantum field theory and curved spacetime that any kind of physically acceptable state where you're going to be able to define a stress energy tensor will have to be Hadamard. And it turns out that the leading order behavior for Hadamard states of a free scalar field at 2 points, x1 and x2, looks like this. And so the 2-point function of the field is going to be inversely proportional. In particular, what's important here is it's inversely proportional to this sigma, which is a square geodesic between 2 points. And so what that means is, as we're considering 2 points that are closer to each other, right? So this lambda operator, whose eigenvalues are used to compute the entanglement entropy of the black hole, is going to take larger values. So it's going to diverge as you consider points closer and closer together. So as we're considering points closer and closer right at the event horizon, those terms are going to dominate this formula. And so the largest contributions to the entanglement entropy will come from those right at the horizon, and that's why you get this area law. Okay, Jacob, just FYI, I see them at 45 minutes, so I'm wrapping up. Okay, so I think that that's important to see, and what that's telling us is that in the black hole case, facts about distances, right, between points inside and outside the event horizon are used to explain the black hole entropy and why it obeys the black hole area law, the Bekenstein-Hawking area law. So we should not think that distances, in that case at least, arise from facts about entanglement entropy. We just shouldn't think that, but here in particular is another good reason why. And my claim is that we should default to think the same is true in the case of the Ryu-Takayanagi area law, because this is another case in which an entanglement entropy is obeying an area law. Here, again, we should default to the assumption that the explanation of this area law also will take distance facts as primitive, since that's so for the other area laws we know about. So it's a case in the Sorkin-Babeli argument I was just talking about, but also it was so for the condensed matter cases that I discussed earlier. We shouldn't think that distances arise from entanglement entropies for this reason in the Ryu-Takayanagi case either. And so I would say, this isn't a bad thing, it's just you need another argument. The burden of proof here is on one who wants to interpret the area law of Ryu and Takayanagi in a very different way metaphysically from these other area laws for entanglement entropy that we think we understand why they hold. All right, so yeah, so I'm not going to be able to talk about this. I mean, the short story here is just like, you know, you need other arguments. You might, so this kind of work of Padmanabhan, Steve Carlup kind of pointed me to, this is interesting, you know, in trying to kind of give some foundation that would allow us to see the space-time metric as being derived from more fundamental facts that are speculative, but that are motivated by claims about or assumptions about entanglement entropy. So this is speculative, but I mean, I think it's interesting and intriguing. So my conclusion. So I've hoped to show here that there's strong support both from within and without the ADS-CFT context for the existence of an important link between entanglement entropy and spatiotemporal distance, right? That's not, I'm not taking credit for any of that work. That's the work of physicists at, you know, hard work that's shown that you have these links. But as a metaphysician, I'm interested in, well, what does that tell us about emergence of space-time? And it seems to me that these results don't lend obvious support for the speculation that the dynamical space-time of general relativity is emergent from facts about quantum entanglement. At least this isn't supported by the work to date. One has to interpret results like that of Ryu and Takayanagi in a way that departs significantly from the intuitions that make them comprehensible, from the arguments, right, the other arguments that made other kinds of entanglement entropy distance links comprehensible, in order to support the claim that space-time emerges from facts about quantum entanglement. So I, you know, read this summer Sean's book, where, you know, he's really optimistic about this, and I think, you know, I think that's where, I'm not saying like don't pursue that, obviously, what's on my business, but I think you just need independent arguments, right? You would use independent arguments in order to use a Ryu-Takayanagi result to make sense of an emergence proposal. And I think this is a move you can make. It's certainly one we should keep on the table, especially as it seems like other routes in developing a quantum theory of gravity do seem to be converging on some kind of emergence hypothesis. But all I wanted to do in this paper was to make clear that that's not what area laws most directly support, at least with how they've been typically justified in physics. So thanks.
Thanks, that was wonderful. Okay, it's on my clock 12:52. I want to make sure that we have a 5-minute break between talks. So I think we'll have time for one, maybe 2 questions. If people would like to raise their hands. I see David Wallace, your hand's raised. Please unmute yourself.
Thanks. Thanks, Alyssa. That's very thought-provoking. Let me raise one possible way in which the sort of symmetry you're talking about potentially gets broken between the entanglement and the space-time side. So in the ADS-CFT correspondence, the boundary is something we've got under reasonably strong control. It's a quantum gravity, sorry, it's a quantum field theory. We know how to do quantum field theories. We know what they look like mathematically. You can plausibly say that we have a sharp characterization of the boundary theory. I mean, that depends on your tolerance for the various mathematical infelicities of QFT, but at least by some standards of rigor, we have that. Now, the interior isn't like that. I mean, we can characterize it as, you know, in its kind of semi-classical low energy regime. We can insofar as it's approximable as GR with cutoff, then we understand the interior reasonably well. But we certainly don't understand the sort of full ultraviolet quantum gravity theory in the interior in an independent way. I mean, if it's string theoretic, we certainly don't have a full characterization of a string theory rather than fragments of it. If it's not string theoretic, we understand it even less well. So, or put another way, we do understand it just fine. We have a perfectly sharp mathematical characterization of the asymptotic ADS quantum gravity. It's that theory which is describable faithfully as a boundary CFT of such and such form. So there's at least a live possibility that there just isn't any way to characterize the interior except via the ADS-CFT correspondence. And even if there is a way of characterizing it, even if there is, for instance, like an exact statement of the interior theory that's not simply piggybacking on the duality, then it's not going to be spatiotemporal all the way down. So at the very least, it's going to have to involve large-scale superpositions of geometry. I mean, if even the low-energy quantum general relativity theory has quantum states that are going to be large-scale superpositions of geometry. and plausibly, depending on your quantum gravity theory, wilder things than that could happen when you start getting genuinely high energy states of the interior. So isn't there a case to be made that for either of those two reasons, the use of spatiotemporal language to describe the interior setup is inevitably a bit rough and ready, a bit low energy, a bit limited to certain quantum states, a bit approximate in a way that just doesn't seem to hold for entanglement facts on the boundary?
So I just want to say that may be so, and so that's if what you're saying is right, that's totally fine. Like what I'm saying here is that you can't just go from like there's this connection to, you know, or the reason why this connection holds even shows us that there is this emergence hypothesis. You need to give other arguments, and like that would be like a way of developing another argument. Like this is why we should think that the CFT is a more fundamental description. You know, or, you know, this is a reason, I mean, the other way you were kind of going at it was, this is a reason to say why a space-time description here isn't the fundamental description. But I guess what I was interested in is, so that's an open question about what to think about the theories of the bulk, right? The theories describing what's going on in the interior. And that's, you know, not something that I was kind of getting into. I was kind of, I think a lot of the discussion, like the papers that I was reading on, you know, like the Ryu-Takayanagi and the papers on holography, that kind of work that I was talking about wasn't really, I mean, it wasn't really working with a kind of like string theory, possibly fundamental theory in the bulk. That's just not what's under discussion. And so there, the question is between this theory that is clearly a description of an ADS space-time, you know, that has a like determinate metric, and then this CFT on the boundary, and how much can we probe, like to what extent can we probe the metric of that space-time given this kind of entanglement features on the boundary? And there, you know, that's kind of what I was interested. So yeah, like go ahead and, you know, give arguments like that. I think that's fine. You know, my kind of interest was in what do these results by themselves establish? And yeah, so like the Maldacena paper is talking about like certain kinds of string theories. That's like, if you look at these other papers, you'll see it's like there's a metric, and then the question is how much can we probe the features of this metric using the entanglement properties on the boundary. And the question is a lot. There are still going to be like entanglement shadows, so places where these extremal surfaces like can't like really go through because of like singularities or something. But you can get a lot of that, a lot of the metric in the neighborhoods of or maybe all of the metric in the neighborhood of the extremal surfaces just by learning about the entanglement entropies on the boundary.
I'd love to come back, I'll save it for later. Thanks.
Yeah, we'll have to come back. If you have further questions, please hang on to them for the question and answer discussion time that we'll have starting at 3 o'clock. So it's 2 minutes to the hour on my clock. I guess we'll take maybe a 3-minute break, and we'll get started with Eleanor Knox at that time. I want to thank Alyssa again for a wonderful talk. So thank you so much. And I'll stop the recording and I'll restart it in a couple of minutes.